In this video, I'm going to show you how to use the checkpointing routine in CrystalGrower. So what do we mean by checkpointing? We mean reading in a completed simulation as a starting point for a new simulation. So you can imagine this as starting from a seed crystal, or if you want to continue growing your existing crystal under different conditions. And you can also use it to recolor your crystal if you want to change the layer coloring that you're using. To use the checkpointing routine, you first have to run a simulation and save a checkpoint at the end of the simulation. So I've got an LTA simulation set up here, which is a tile-based simulation, and I've just set it up with some standard energies, so no screw dislocations, although you can use those if you want with the checkpointing system, and no additional features, but you can use these again with the checkpointing routine. So I'll just go through the tabs and show the settings that I'm using. They're all fairly standard: high temperature for a zeolite to grow, 1 frame for the movie. I'm running in mode 3, so at the end we're going to be at equilibrium. And then my tile energies, I'm using energies that we've already found with previous simulations for zeolite A. And crystal coloring, because I haven't run a simulation yet, I'm going to use the find mode to color it. But I'll show you how to use the checkpointing routine to recolor your crystal. Okay, so we'll run our simulation. So now that the simulation's finished, we need to load the checkpoint at the end of this simulation as the starting point for our new simulation. So let's go back to the structure options page and now say that we do want to load a checkpoint file. We now have to find the file path for the checkpoint file that we want to use. So we'll go to the LTA simulation that we just ran, and we'll find the file marked checkpoint, and we'll load that. Then we can click read checkpoint file, and it will tell you if you've loaded the checkpoint file correctly. For a tile-based system, we can change any of the settings we had across a checkpoint. So there are no fixed options. We could change any of these if we want to, but it can't automatically allocate memory once you're loading a checkpoint. So we have to actually define the memory space that we want to use. Whereas if you want to start a simulation from scratch, you can automatically calculate the memory requirement for your simulation. So as we're going to grow our crystal a little bit larger, we should increase this. But we're going to grow at a lower supersaturation, so it's not going to grow much bigger. So I'll change this to 251. And I'll make all the dimensions the same. So you can change your tile energies, but I'm going to leave them all the same. But I am going to change the supersaturation profile. So I'm going to switch to mode 5 instead, because I'm actually starting from this end point here. So at the end of this first simulation I ran, the crystal is going to be at equilibrium, so we're actually going to start here. So I'm going to use mode 5 to set some delta mu's around this point here. Let's say I wanted to grow my crystal slowly and then dissolve it back a little bit slowly at the end during this checkpointed simulation. So I'll switch to mode 5. But I now need to define my delta mu values that I'm going to use. So we need to find out what the equilibrium point was of that previous simulation. So I need to look at my delta mu file within the simulation output. So I'll open the simulation and I'll open this delta mu file here. If I scroll right down to the bottom, I can see that the delta mu is around 15.55 on average, because the last part of the simulation was at equilibrium. So I know that my 15.55 is my 0 for a tile-based system. In net-based systems it'll be closer to 0, but in tile-based systems your 0 is defined as your bulk crystal level, not your site that's in equilibrium with the solution. So if I wanted to carry on growing this seed crystal that I have from my checkpoint at a low growth rate, I can set my delta mu at about 3 kcal per mole above equilibrium, so we'll go for 18.5. And then if I want to dissolve my crystal slightly, I can put it below equilibrium, so I'll set it 3 kcal per mole below equilibrium as well. So that will be 12.5 kcal per mole. So let's input that into CrystalGrower. So delta mu 1 will be 18.5, and delta mu 2 will be 12.5. And we'll give them both an equal length in the simulation, so half the simulation growing slowly, half the simulation dissolving slowly. Now if we want to actually see that, we should probably make a movie. So I'll just make this a movie, and I'll take 10 frames across the simulation, just so we can get an idea of what's going on. Because we ran the first simulation in find mode, we now have a layer coloring file that we can use. So I'll click color, and I'll browse to find the facets found file from my last simulation. But before I run this, I'll just check which facets have been picked up. So I'll open the file in the editing window as well. And I'll click read layer file. And that'll show me all the planes that it's picked up. So it's picked up too many here, but we'll edit this when using the checkpointing system to recolor the crystal. So let's run our checkpointed simulation. You can see that it tells you it's reading in the checkpoint. It says the checkpoint's processed, and you can see now it's outputting the frames. So let's open up our first simulation and compare it to our second simulation. So if we open the XYZ file from our first simulation, you'll see we have this crystal. Then if we move and open up our second simulation, you'll see that the start of the second simulation looks fairly similar to the end of the first simulation, which is what you'd expect when you read it in as a checkpoint. There is a slight difference because the crystal will have grown for 100,000 iterations before the first frame was captured in the second simulation. But you can see the morphologies are generally the same. So let's watch how this simulation progresses. See, it's growing slowly at the beginning and then dissolves quite rapidly at the end. Because a delta mu of 3 kcal per mole is quite a large driving force. So let's look at now recoloring this crystal using the checkpointing routine. So we don't want to run a whole simulation again because the crystal morphology will change. So let's try reading in the first simulation again and just recolor and tidy up this crystal a bit, as our crystal started to dissolve a bit in our second simulation. So let's go back to CrystalGrower and recolor this crystal. So our simulation is still set up to read in that first simulation as the checkpoint, which we want to do for this recoloring example. We don't want to run the simulation again because we know the crystal will change slightly. We just want to run it for another 2 iterations so it reads in the simulation file and then spits it back out with the new coloring that we've decided. So let's change the number of iterations. Let's make this really small. We only need to run it 2 iterations and we just need a single frame. We can leave supersaturation profile the same, doesn't matter. We can leave the tile energies the same, but we're going to change quite a bit on the crystal coloring. So we're going to need to edit this file quite a bit. So let's decide where to save our edited file. So we can click this browse box. I'll save it in the original simulations folder. I'll choose that, but I need to give it a file name, so I'll call it LTA edited facets.txt. And now I'm going to remove a lot of these facets. So I know from experience which facets are shown here. You have your 100 set of planes on the main faces of this crystal. Then you've got the corners missing, so that's your 111 facets. And then you've got your edges missing as well. That's your 110 facets. Depending on the heights of these terraces on the crystal surface, it might be halfway between these planes, but that's a good guess to start with. And we're not trying to get this perfect anyway, we're just trying to tidy up the coloring. So we don't want to keep 4 00s and 3 00s and 2 00s. We can just remove these. So let's cross a few of these off and just leave the ones with 1 in them. So we should have 6 main faces, which are the 100 set. We should have 8 corner facets, which are the 111 set. There's the 8 up here. And then we should have 12 edge facets, which is the 110 set here. So a total of 26 facets. So now let's save those changes. And then we can browse and use that as our new coloring. So we'll load this edited facets file as our coloring file, and then run CrystalGrower. And then you can see it just runs very quickly and then it's done. So if we compare the two simulations side by side, I've already opened them. You can see that the coloring is slightly improved in the second simulation versus the first. To improve it further, I can lower the number of layers colored on each facet. So you can see there's 4 colored here, which starts to eat into the other facet. So we can reduce that down to 2 or 1. So let's do that quickly now. Focusing on the 1, 0, 0 set, let's reduce all those down to 2. And then I'll save over our current file, press run again. And then we can load this simulation and compare it. You can see that one's even tidier. So now you can see between those two that the layering here is much better. You can also run net type structures with the checkpointing module. So here I've just set up a simulation for barite, an ionic crystal, growing at room temperature. I'll grow for 1 million iterations. And I'll grow in mode 5 with these interaction energies. And I'll color using a facets file that I already have prepared. So I know that these 6 facets appear in this crystal morphology. So we'll just run the simulation. And now that this simulation is complete, we also have a checkpoint file, so I can read that in as an input for my next simulation. So I'll say yes to load a checkpoint. I'll find the new barite checkpoint file I have, which is in here, and I'll read that checkpoint file. It works almost identically to the tile simulation we just ran, but there'll be certain things that you can't carry over. You can't automatically allocate memory when you're using a checkpoint, so I'll set this slightly higher, 251, 301, and we'll do 201 there. Because we're going to grow a slightly larger crystal, this might be overkill here. You also won't be able to change if your system is grouped when you're using a checkpoint, because this changes the number of sites that CrystalGrower has to consider, which is a key thing carried across between checkpoints. Again, we'll try this time growing the crystal slightly larger, based around its equilibrium point that we know is going to be roughly 0 for a net crystal. We'll grow it slowly at about 3 kcal per mole again. So if we go to net options, you also won't be able to change weighting across checkpoints for net-based systems. This again affects the number of sites that CrystalGrower has to consider, which is a crucial number carried across between a checkpoint. Any of the other parameters can be changed, however. We'll use the same coloring file, but to differentiate between the simulations we'll change the number of layers on these 2 facets, so we'll halve them down to 5. And then we can run our simulation. So let's visualize our 2 simulations and compare them. So on the left we've got the file the checkpoint originated from, and this one on the right is the crystal that we carried on growing from this seed crystal on the left. So you can see that the right one is larger, almost double the number of particles, and you can see there's a number of new terraces on the surface, some smaller ones, and some small surface nucleations. So that's a few examples of checkpointing, how you can use it to grow a seed crystal or to recolor a crystal. If your simulation fails because it reaches the box edge, provided you've enabled checkpoint saving, it will save a checkpoint at this time, so you can then load that simulation into a larger box if you want to carry on growing it. So that means you don't waste any simulation time. You can change parameters across simulations. For example, if you want to change temperature, you can do that between checkpoints. Delta mu modes, delta mu excess, anything apart from the things mentioned in this video that you can't change, you can change them across a checkpoint. So hopefully you can see how checkpointing is a useful tool to use across lots of simulation areas.